I think we can get started. I just got a new laptop, well, a month ago, and I'm not sure I'm going to play with changing the screen resolution now, but I do notice that it's a little off there. But I will be partially using some slides and also using the Blackboard to go a bit in detail. I'm going to give 4 lectures, in fact, on quantum error correction. And 3 of these lectures are going to take place this week. And then the 4th lecture is going to be in June at the school in Chalmers, because I was asked there to talk specifically about surface code architecture. And so it means that I won't say that much about the surface code in these 3 lectures. And instead, I'd like to give you kind of a wider perspective on quantum error correction. Now, maybe David already did this. I have no idea what kind of classes you have followed in quantum information. I assume you have already done some of that. And probably, maybe, let's see, who knows what the surface code is? Probably a lot of people. Yes, okay, good. Okay, so because the surface code sort of has entered the popular realm, I would say, whereas some of the earlier work in quantum error correction you may be less familiar with. And I think it's of interest to actually also learn about this. So that's what I'll try to cover a little bit in these lectures. Okay, so the first, so today I want to talk about noise models, about the quantum error correction conditions. Who knows what the quantum error correction conditions are? See, there's a whole different, David knows what okay, he's the only one. Okay, so, okay, at least I'm telling you something that you don't know yet. So, and then some small miscellaneous codes we'll discuss. Okay, so, yes. And so I can nicely refer, I wrote a review on quantum error correction that is about to appear in this year in Reviews of Modern Physics that, of course, I can very much recommend to you. And if you spot any errors or mistakes, then please let me know. And I hope you get something out of it. Okay. So what are we going to discuss? Now, so I feel like you guys are sort of a new, young generation with, no preconceptions perhaps as we have developed and new, fresh ideas. And I can imagine that you've all asked yourself the question, maybe you're an experimentalist and you work with some solid state qubits that have coherence times that are maybe order, tens of microseconds. And you ask yourself, how the hell am I going to make a computer out of this? And I don't know what your take is on whether this is actually feasible. I sometimes get asked these questions, you think a quantum computer can be realized in future. Of course, these are hard to answer. And typically, the answers that one gets are like, okay, maybe in 30 years. And of course, 30 years is exactly the time window beyond which one cannot, one no longer is going to check back what you predicted was going to happen. So it's safe to say, after 30 years, this will happen. It also means that I basically have no clue whether it's going to happen or not, and I just put it somewhere in the future. That is at least not excluded. So who here maybe, I don't know, I'm going to take the opinion of somebody. So who says, well, I really think this is just complete baloney. I mean, this is never going to happen. It's a nice idea, but I'm very, very skeptical. Ooh, people are not. And why you're optimistic about this, right? I mean, look, you have a qubit that lives for 10 microseconds. How are you going to make that into a qubit that's good for an hour, a whole a month, a year? So how would you do this, right? I mean, of course, the answer is error correction, but maybe you don't think the answer is that. Topology. But what do you mean? So Mariana fermions. But there's actually experiments, I think, that says that parity of the number of electron switches in milliseconds. So maybe if you get this Mariana fermion qubit going, maybe that also will have some fairly short lifetime. No? I don't know. I mean, so any ideas? I mean, Or I mean, why you're optimistic, right? Because you're told that it's supposed to work in the future.
But it's also a question, how long time do you need this then?
Right. I mean, of course, yes. Yes. Right. So indeed, it also what can you do in that time window? Yes. But of course, if you say I want to get a whole computation over with, which has many operations, 1 millisecond is not enough, right? So. Okay, so the thing, of course, this is a question that has been asked before. And I want to go back to 1956. So I actually want to have two historical slides. One is the year 1946. Actually, maybe we do that first. So this is the first, electronic general purpose computer, the ENIAC, which you probably have heard about. And I just took this from Wikipedia, and I thought it was just sort of nice to see what a huge, this is a huge machine, which weighed 27 ton. It was, this thing unfortunately dropped off, just 2.4 meters by 0.9 meter by 30 meters. And it also consumed a lot of power. And of course, the reason to say this is that if we ever have some prototype of a quantum computer or something that does quantum computation, that it's awkward and large, we shouldn't be ashamed of, right? I mean, if you see this, and it's also likely to consume a lot of power, but that doesn't mean that would be the final device. So that's sort of hopeful. Although, if you imagine that you have to put that thing in a fridge at a few millikelvin, it's kind of it's a bit more challenging. So this machine, this machine cycle was 200 microseconds, and in those 200 microseconds, it could write a 10-digit number, read a number from a register, and add and subtract two numbers. So very basic logic. And so you could also ask, would that quantum computer run in a comparable time? Now, of course, now we work on elementary gates. Of elementary logic gates that may be taking tens of nanoseconds. But if we use quantum error correction that we're going to discuss, we expect that the logical computation and the physical qubits that we build now support logical qubits, and the gates that we do in those logical qubits will be run at a much slower rate. You may expect, this is a very, very rough estimate, I don't know. So there are papers that say for superconducting qubits that you get error information every 200 nanoseconds. And in order to do a C0 gate, you need to gradually change where you get your error information. And how many of those steps you do depends on the code that you choose, how much physical qubits comprise one logical qubits, which depends on a parameter L. So if L is 100, say the C0 gate to order 100 cycles, you come to 20 microseconds. So it could be, which is very, very rough. I just put this in, this morning, so I don't necessarily say that this is a very deep insight. But at least you can imagine maybe this clock speed could be similar. Okay, but this ENIAC also supposedly failed. Sometimes it wasn't the end of the story. And let's now go back to 56. Because, of course, that was with vacuum tubes, and the whole, developments of chips has led to, tremendous improvements and computational power, throughout our lives. But von Neumann asked himself a question, I think, primarily about biological systems. Because that we are full of, failures and errors is sort of more clear than maybe if you talk about now, modern computers. So this is a paper from 1956. So concerned with the synthesis of reliable organisms from unreliable components. And so those are, in essence, you could say, the ideas that we should try because we may not have any better ideas. Perhaps topology will come to the rescue. But otherwise, we have to somehow engineer ourselves away, and we may need these kind of ideas. And these ideas are the ideas of quantum error correction and fault tolerance. And so in this page that I took out of this paper, the basic idea is very, very simply demonstrated. I don't want to show you all detail, but so let's imagine one have one process, process O, which takes some input, and it also has two outputs. Instead of running this once, we just make 3 copies of this process. So O is a given network, and we construct O in triplicate, labeling the copies O1, O2, and O3. And then, so out of these 3 copies, we have 2 outputs, and we feed these outputs in a new organ. He calls these organs in this paper because the idea is it corresponds to some kind of biological system. Well, I guess that's what, yeah, it's a biological system. So this organ M is the majority organ. So it just takes the majority of these 2 outputs. And then he estimates when this type of precision, and then you can do this recursively, because now you can call this new thing with 2 outputs. And the inputs here, there's a copying of these inputs to these different organs, right? So there are 4 inputs that each organ takes, and they're just copied down to each of these guys. So this is now a new unit with 4 inputs and 2 outputs. And you can, of course, repeat this procedure, right? So this is a new organ O prime, and we take 3 copies of that, and we feed their answers in the majority function and repeat. So is that a clear idea? So in this paper, he analyzes. So he says every one of these organs at the basic level, this is some unit does some little computation. It has a failure error. It's a probability for failure eta. And these are identical for these copies. And let's also assume that this majority also has a failure rate. And then he wants to estimate what happens when you do this repeated process, and what is the failure rate after recursively doing this, at the top level, right? And do you get something? And of course, what you want is that failure rate is not going to a half, right? Because then it's completely noisy. So he first of all he estimates that, like I said, I'm not going to this majority function M should fill with a probability less than a 16th. So otherwise, the whole you're never going to get where no error rates of here, or you're going to get good behavior. And then there's a little plot. So this is eta is the error rate of one of these 3 units, and eta star is the error rate of the new unit, right? So let's say we take an eta that is has an error probability less than a half. So we start here. Then we get an error rate eta star. And we feed that back so we can go this way. And that becomes the new error rate that we start with at the next time we do it. So if maybe I should draw this instead of pointing to it. That's a little, okay, so there's this line where they're equal. And let's assume, so he has some curve that looks like this. So say we start at some error rate over here. And so the new unit, the compound unit, will have an error rate which is this. Yeah? And this chalk is really not so, it's too soft. Okay. And so in order to, maybe I should have chosen it a little bit over here. Okay, so I'll start over here. I take this one. I go there. And now this is my new unit. And so you can, if you recursively do this, you see that the you flow towards this point. Right? So do you understand what I'm doing here? I'm saying I have a basic error rate eta of these units, and let's assume there's some function that is plotted here, which says given an error rate of this majority function, which I've fixed now, which is less than 60%, I get of this whole thing, which has 4 inputs and 2 outputs, I get a new error rate. Yeah? And then I feed that new unit, again, in such a construction, I see what I get as a new error rate. And then I see where this flows to if I keep on repeating this. And what this thing shows is that if you're below a half, you always, if you keep on doing this, you flow to this point, which is this, which is called epsilon 0. Yeah? So if you keep on doing this recursively, you will get you'll get a noise error rate which is epsilon 0. Yeah. Okay, so that is roughly what he's doing in this paper. You can have a look at it. But that, in some sense, is also the basic idea of one basic idea what one can use in constructing a fault-tolerant quantum computer, which is the idea of concatenation and recursively coding, using a code to improve your error rate.
Sorry?
Yeah.
This graph for this specific example, because I don't understand why it doesn't go to 0 for...
Well, I think this also has to do with this error. I mean, okay, so that is not so clear because indeed, usually you actually do get this something asymptotically going to 0. Yeah, if you apply this for quantum codes, your error rate asymptotically goes to 0. Now, the reason why this function in his case goes like this, I don't actually know. Okay, so we have to take this a bit of as a heuristic example. Okay. Okay, but this is just to demonstrate to you that this idea of error correction fault tolerance is actually a very early idea, but it's never been, in some sense, so necessary when the making a computer. This has not been a very crucial step, but we anticipate that for a quantum computer, this may be a very important step. Okay, so the idea is with error correction, you use many elementary qubits to encode or to create one better protected qubit. And the problem is that unlike in the classical case, which I just showed you, by which you say I repeat the process 3 times instead of having a bit which is 0, I have 3 bits which are 0, and instead of having a 1, I have 3 bits or 1. For quantum code, this is more complex. So for quantum code, this majority function taking is more complex, and the description of how you add the redundancy is more complex. And that means also that because it's more complex, it takes more elementary gates, it's harder to get it to work. Yeah? So the noise threshold, which we'll come to later, which is, you could say, is related to the 16% in this von Neumann scheme, is typically much, much lower than what you would have classically. Okay, but now, so what I want to discuss now is noise models. And I think what is interesting, so what I want to do, so there are noise models that we obtain from a physical description of the system. And I want to connect them to properties of error correction codes via the quantum error correction conditions. Now, very simple noise models, when we do numerical simulations of how codes perform, we assume very simple noise models. We typically assume that the noise acts independently on different qubits. Perhaps if 2 qubits go through a 2-qubit gate, we need to describe the noise on both qubits that may be correlated. We also typically assume in these numerical studies that the noise, there's no memory. So the noise is Markovian. So the environment, if we want to describe the noise using an environment, rapidly forgets, what noise has happened. So we can describe the noise by a Lindblad equation, say. So of course this is not always true, and it's, I think, an interesting challenge also, I think, for the future to actually connect the performance of a code more specifically to the noise that we expect in an experiment, that we get really out from a detailed modeling. Okay, so there is also a focus on poly errors, and I also like to motivate why that's the case. Okay, so now let me start with some writing on the blackboard. See, I don't want to get this too wet. This is not such a good thing. Sorry, I just have to figure out what the optimal setup is here with the squeegees and so on. Okay, now if we're going to talk about quantum error correction conditions. And these quantum error corrections are stated or phrased with respect to a superoperator. So, and I'm going to focus on, imagine this is a superoperator acts on 1 qubit or 2 qubits, some low number of qubits. And now I assume that but this, okay, does not need to be trace preserving. Let me see. Okay, so in general we have. I assume that you're familiar with superoperators. Is that correct? Who has not seen a superoperator? Okay, well, nobody dares to say anything. Okay, so so you can imagine that if you'd have a detailed description of some gate that you're doing, let's say you're trying to do a high fidelity 2-qubit gate, that you could try to describe what happens instead by the unitary representing the gate, followed by some superoperator S, which you'd like to be close to the identity gate. So this is just a composition of these things. Yeah? So we actually, let me say, I just want to show you this. So in preparing this lecture, I came upon a paper that I've written with a few other people, which is actually a very nice paper. So yeah, it's like, hey, geez, looks good. So what we did in this paper, I don't want to advertise this paper. So this was working actually. We were doing an analysis of an IBM oscillator stabilized flux qubit. So there's a qubit that's no longer in fashion, right? It wasn't good enough. And we imagined what would it take to do, universal quantum computation there. So we wanted to do a C-phase gate, single qubit preparations and measurements. And we wanted for every one of those components to analyze the, most accurately the noise. So the idea was that for every one of those components, we'd like to have a superoperator description. In this form with the gate and the superoperator. And in fact, we wanted to separate the superoperator out in terms of parts which were leaking. So instead of staying in the computational subspace, the 0-1 level, you go out of it. There were dephasing errors that we wanted to treat separately from amplitude damping errors. I'll come to these things in more detail. And we did some of that, and we wanted to estimate an error rate for every one of those components separately. And this first goes beyond the sort of simple, depolarizing channel that you may have seen before. And also we actually, maybe I want to say one more thing about this paper. We also want, and I mean, this is just maybe a little advertising, but I think there's some nice ideas in this paper in the following sense. So our take on this was saying the gates that we have, we saw that the source of errors was mostly dephasing errors. So so the noise was biased. Yeah. Now the problem is that you say, okay, well this is kind of generally, this is more generally true, right? Your T2 typically is much shorter than your T1. And can you take advantage of that in designing your code? This is the question. So you'd like to have a code that corrects more dephasing errors than bit flip errors. But this is not entirely trivial, because when doing your error correction, if you do the Hadamard gates that map bit flip onto phase flip errors, you convert, so you mix these error rates. So you have to be careful in designing your error correction circuitry not to get bit flip errors at the rate at which the phase flip errors were happening. So that was a challenge, and there was some more theory work on this. And by now this is, well, I'd say nobody is really pursuing this, but I don't see why actually maybe we should also be thinking about this. Not only about the surface code. So this is basically the theme of my lecture, that don't only think about the surface code. Okay. Anyhow, so that was about that. But okay, so what do you want to say about the super operator? Now, how we get this super operator typically? Well, one could get it from a Lindblad equation. So if our environment is Markovian, we have some, we start with some, and typically, if you have some, for many cases this well. Okay, so let me just write down. So maybe I should ask a question, because I can do this and I can also not do this. So do people know, if you have this Lindblad equation for a very short time, how to get the super operator that corresponds to it? So the idea is that you can integrate this equation, right? You have rho of t is either let's call this is L on rho is some operator. Let's say this is time independent, the Hamiltonian, and the quantum jump operators. So let's say this is T0. So there's some time dynamics of the system which always maps the density matrix onto the density matrix. So for some fixed time, there should be an alternative description in terms of a super operator. Yeah. So have people seen this? How you take a short time and then obtain these operation elements from these guys? Yes? No? Mixture? Okay. Okay, maybe I can just go mention it briefly. So, okay, so we want to do this for some short time. T is epsilon. If the time is short, this is e to the L epsilon. So I expand it. Can people read this? And now I can just apply L on rho of t times an epsilon. This maps. So this is rho of t0 plus epsilon L on rho. And L on rho is all of this. Yeah. Now, I've put a Hamiltonian here. It could be, that's the Hamiltonian I'm applying to do a gate, or it could be this just a free evolution of my qubit. Let's imagine this is an equation for a single qubit. And I could also go to a rotating frame in which I rotate this away. It's no longer there. And so now what is let's imagine that my H, so my H now assumed to be 0. And so then if I just look at, so I define an operator. Okay, so maybe I'm just going to say that I'll give it to you, and then you could verify this yourself. Okay, so the point is, if I start from the limit equation, it's quite simple for short time to get a superoperator picture. Why would I want to get a superoperator picture? Well, then I know what the errors are. Because the superoperator, if I have a code, so for the superoperator, I can get a noise rate, even if it's not a poly channel. I will show you that in a moment. And I can also see if I've chosen a certain code, how well does it do with respect to that set of errors. Yeah? Now, of course, this limit equation could be running for a long time, and then these operators may have a more complicated description. But for short time, they're fairly simple. So there are error operators. They're just proportional to the quantum jump operators. And there is the no error operator. And the important point of the no error operator always is that it's close to the identity, but it's never quite the identity. Yeah? And this becomes, well, this relates to that the equation has to preserve complete positivity. Okay, so I get a superoperator description this way. Now, I presume, so very simple, of course, a very simple noise model is what I refer to as the polarizing noise. Already running out of board here. The polarizing noise. So then, in such a case, I have with probability 1 minus p, I have no error. And with probability p over 3, I have, say, an x error. With probability p over 3, I have a y error. And with probability p over 3, I have a z error. And for the polarizing noise, of course, it's very clear what I call the error rate. Yeah? But now, if I have a superoperator on a qubit, let's say with operation elements AI, okay, it's an arbitrary operator, right? Well, it has to obey this condition because the superoperator has to be trace preserving, but otherwise there's an arbitrary operator on a qubit. Now, an arbitrary operator on a qubit can be written as a linear combinations of Paulis. It's just because these Paulis are, basis for this, these 2x2 matrices. But then it's not so clear what I should call the error probability, right, for such a thing. If these AIs are some linear, each of them is some linear combination of the identity and some Pauli. Right? So how should I properly define this? Okay, so the way you can define this, which we did in this paper, it was done elsewhere also. You want to keep this, let's see, if people take notes, or maybe I can fold this over then. Yes? So what you do is you have your superoperator S, and you write it as, so it's some, AI, rho, AI dagger, and you write it as something which is the, let's call this N for noise. This is the identity map. So I on rho is rho for any density matrix. Okay. So you take, and this, okay, so the idea is the superoperator is, part of it is the identity map with some coefficient in front. This coefficient may be different from 1. It could be, it's actually, it should be trace decreasing. So alpha trace decreasing. And some n. And now the error rate, or the error strength, how do you define it? epsilon is a norm of this operator n. So that's the part that you don't want, because you want it to be close to the identity operator. And this is with respect to what is called a diamond norm. It doesn't matter much, because I'm just going to give you the definition. And I'm going to give you the mathematical definition. In practice, of course, this may be hard to evaluate that. This norm is something, I'm taking the maximum over all density matrices, and I'm applying this noisy operation on, let's scale. Okay. Okay, so let me just say this in words. Let's imagine this noisy operation acts on a qubit. Now, I could say, well, then this norm is basically, I apply it on any density matrix of a qubit, and I just look at the trace norm of what I get, how big it is. The trace norm is probably a quantity that you've seen. But there's a slight change, which makes it a stable norm. I mean, this is just in mathematical analysis important. Maybe in practice, you want to cut some corners and not apply this to any density matrix. But the mathematically proper definition is you apply the noisy operation tensor, the identity, on a density matrix in a larger space. Yeah? So the idea is that this space would be at least, or should be, if this is a qubit, this would also be a qubit. Okay, so you're not only looking at density matrices in the systems itself on which it acts, how much this noise does, but you're looking at it also if the density matrix is part of a larger system. And that's not the same necessarily. The norm of, this is not the same quantity if you were taking the max over all rho with rho only a density matrix on this, because it could be entangled between these two. Yeah? Probably this is something that you haven't seen before, but yeah, so that is the error strength that we actually, for those things, we worked through. We estimated some error strength, and you can apply that to super operators that are not necessarily of this form. Yeah? So if you so typically, if it's a simple form, this error strength is like your probability of error that you would, as you would expect. But if you would have another, noise description that we'll come to, like amplitude damping, you get some other quantity. Okay. Now, okay, so I want to. So are there any questions about this? Does the people understand what is the definition here, at least? Maybe they haven't. Because this is awkward, of course, you have to take the maximum over all density matrices and so on, so you have to do some optimization. So maybe in practice it's not so useful, but of course with fidelities also there, you may sometimes have to do optimizations. Okay, now I want to say one more thing about noise, because okay, so if we have some Lindblad equation, I can imagine, and some, we can imagine that this, we may work ourselves towards some super operator description. Is this going to work? But one very, ubiquitous source of noise is also, classical, fluctuating classical parameters, in which we don't really say there's a quantum environment and we trace out over the environment. No, we first start with, classical stochastic variables that influence the qubit parameters, like 1 over f noise. Now, and what I want to say about 1 over f noise is it's a kind of an incomplete story. I can say a few things about it, but I don't think anybody has really taken this into account in well, in a very rigorous fashion. The problem, of course, with 1 over f noise is that it's very non-Markovian. It's slowly fluctuating parameters. And so it's this idea that you can get a super operator for a short time interval that cannot fully capture the correlations in the noise. Yeah? So of course, if you've done already some refocusing and you've gotten rid of some of the 1 over f noise, you may make your noise effectively Markovian, and such a picture would again apply. Okay, but so let me say something about 1 over f noise. In the sense, make a very simple remark, which I think is often for people that are not so, Okay, so let me tell you why I want to break the remark. Okay, so people usually, maybe they learn about quantum error correction and say, okay, there's bit flip error, there's phase flip error, and there's both. And then the first question you ask yourself, or you should ask yourself, look, I don't have that kind of error. If I have a gate that it just have a small over rotation, or the frequency of my qubit is just like, it's jittering a bit. What does this have to do with Pauli errors? It doesn't at all look like Pauli errors, right? Pauli errors, is a discrete set of errors, and what I have is just a little error all the time. Yeah. So what's the motivation? Why, if you talk about codes, you say I can correct Pauli errors. Why do you say you're done? Right? Because why does that cover my source of noise as well? Okay, so I want to illustrate that by a simple example, and yeah, okay, so let's do that. Well, what do I want to say about 1 over f noise? Do I want to say anything about it? Okay, so let me maybe skip the 1 over f noise, because I can't say that much about how one handles the long-time correlations. Because that would require you to have a description in terms of a super operator for a long time, right? If you want to really take into account the noise correlations. So let's imagine I have some, I have my Hamiltonian, h bar 0, and this parameter is drifting. Yeah? So this is really some basic frequency that I calibrated my qubit to, but then it's changing over time, and there's the average fluctuations are 0, but there is some and there's some correlation in time that I'm now sort of dropping. But I could say for such a small thing, I could say, well, maybe there's some probability distribution. So I'm not taking into account time correlation. So I'm just saying for a short interval in time, I have a certain probability distribution over these frequency shifts. Yeah? And maybe that's some Gaussian centered around so P of dW is 0. So instead of, if I just let my system evolve for some short time t, then I have it evolve as expected, but perhaps that I have a small over rotation or under rotation captured by delta W. So I could capture that as a noise model where I have my ideal rotation, which is this, composition, which is just doing after some error operator, some super operator, which I just describe by and I can't fit it in the board here. Okay, so is this clear? Okay, so let me say the words. E on rho is just the average It's an integral over all, well, d omega. The probability for d omega, and then I evolve with my small d omega. Is this clear what it's? Sorry, you can't write it, but this is just u and u dagger. Yeah, of course, this is only for, and this is some Gaussian distribution. So now I need to erase something. Okay, so now maybe I'll just use this board. Okay, yeah. Okay, this is the right chalk. Yeah, but now we can use the fact that the Pauli matrices form a basis, right? Well, everybody knows this. So I can expand every one of these. So I just write this small over-rotation as a linear combination of something proportional to the identity, times the cosine, plus something proportional to z with the sine. Yeah? And then the point is, of course, that if this delta omega is truly small for this time interval t, then this is fairly large and this is small. So if I write E of rho, like I said, what we want to do is we want to expand, before we were talking about error strengths, I want to write my noise as something that's proportional to the identity operator plus the noisy stuff, right? And so the identity operator part, so this is definitely d omega p omega cos squared d omega t times this identity map plus, well, that's my noisy map that I've lumped together everything else, right? I put in this here on both sides, and this thing has at least a sine delta omega t in it. And of course, this is very small. Yeah, so the point is that, okay, so that is the point. I can, any small error, small shift, small drift, I can expand in no error and a big error, and express the smallness of an error in terms of an amplitude or a probability or an error strength at the end of the day, yes? Yeah, so the fact that this is a small drift gets reflected into the error strengths of the noise operator n, which I don't work this out here, but one can. Okay. Yes, I guess I'm going too slow. Yeah. Doesn't matter. I'm going to continue now. Yes. So I gave you a little bit of an idea. Okay, so I talked a bit about noise models because I want to connect it to the properties of a code and what a code can do. Of course, we can take an experimental point of view. We say, well, we just encode the qubits and do measurements and see, how well we preserve our data. But of course, we also like to, in advance, before doing the experiments, get an idea about whether that code is likely going to be successful. So I want to discuss the quantum error correction conditions. First, I have to say, what is a code? Yeah? Okay, so in the classical case, well, okay, so what's a code? It's, if I want to say I'm encoding a single qubit, into many more qubits, what it is I specify a two-dimensional subspace in a large space. Let's imagine I have 3 qubits, because I'm going to do a 3-bit repetition code. And so that's a 2 to the 3 8-dimensional space. And my qubit has to live in a 2-dimensional subspace thereof. Yeah? And in that subspace, I can define a few states. Just conveniently, I can call one state the logical 0. Everything that's logical has an overline on it. And there's the logical 1. And these states are orthogonal. And I can write down perhaps what these states are in terms of my 3 qubits. Let's say for the repetition code, which is always the trivial example, if I encode, so my logical 0 is 0, 0, 0, and my logical 1 I call 1, 1, 1. Okay. Then I can also specify my logical operators, which are just by definition operators that have a certain action on these states. Of course, what I call my 0 and 1 is kind of up to myself, but once I fix that, then there's an operation that maps this onto that and vice versa. I call that the logical x, because it flips the logical bit. And how do that logical bit flip operator can again be expressed in terms of actions on the 3 individual qubits. So in this case, the logical x has to flip the first bit, the second bit, and the third bit. So the logical x is x1, x2, x3. There's also a logical z and a logical y. But logical y I get when I have the logical z. So the logical z has to map the plus, okay, so let me just erase this. So the logical z has to map 0, 0, 0 plus 1, 1, 1 onto 0, 0, 0 minus 1, 1, 1, and vice versa, right? Because it has to, by definition, it has to map the plus state on the minus state, or you could say the logical z is, the 0 and the 1 are eigenstates of the logical z with plus or minus eigenvalue, as I say it there. Okay, I will come to some of these things later when we discuss some more complicated codes. So for now, the code is just a specification of a subspace. So now I can formulate my quantum error correction conditions. Now, why you don't know about quantum error correction conditions, I know there's a reason for this. It's because they are hard to verify. And what you probably have learned about is stabilizer error correction. And for stabilizer codes, there's much simpler way of understanding what errors the code can correct. And you can these quantum error correction conditions kind of forget about. But I think they are still valuable and interesting, especially when we deal with non-Pauli errors. What I mean by that is that when my super operator that is describing the noise that I actually have in my system, these guys are not Paulis, there's sums of Paulis, right? Linear combinations of Paulis. And there's no reason why they should be Paulis. Maybe it's just a simplified model that we like to deal with. It's also a useful condition if you talk about approximate error correction. This is also something that is much more practical than the theory of error correction. So approximate error corrections, you say, well, I have a bunch of errors which are specified, the specification of these operators AI, and I cannot correct them perfectly. Now, I'll tell you what it means to correct errors. Then these error correction conditions that I'll tell you, they will be fulfilled approximately. They will be fulfilled up to some order. There'll be some remaining terms which are small, but which would violate these conditions to be true. Okay, so we assume the existence of a super operator description of our noise. Now here I've called these these are called the Krauss operators, EK instead of AI. And this is not necessarily trace preserving, so that's handy. And how do I get this? Well, okay, I may have to do some, some earlier analysis to get to this description. And I want to analyze, let's say imagine, so I want to know whether a certain code, which is a subspace, so the super operator acts on a bunch of qubits. Yeah? Let's say n qubits. And in that n qubit space, I've specified some code space. I have taken some bit strings, k bit strings, maybe k is 1. And I have mapped them onto encoded bit strings. So in this case, my n is 3, and I encode 1 bit. So this is, z is 0 and z is 1. And so the error correction conditions say something like this. One can correct a set of errors EK, or any linear combination of these errors, I come to that, if and only if for all k this is true. And we're going to stare at this a little bit, because if you look at it like this, it doesn't tell you very much probably. So one thing we'll see, so what I want to do, and I don't know, it's the end of the day and I'm already going slow, but I do like to do this. I want to actually show you how this is proved. This proof is done in Nielsen-Schwang. It's not very hard, but it gives you an intuition about why this is true. Yeah? And this is the theory school, so we can go all out on theory. So, so what does these conditions say? Let's look at them first before we start. So there are two ways of looking at it. So first of all, let's say there's two ways of reading these equations. Let's take z to be z and z prime to be the same. Then I have a condition that says for all z's, so for all bit strings that I encode, the expectation value of that operator ek dagger el is some alpha kl. Yeah? Okay. Now, what does that say? Well, what is important, actually, the alpha KL does not depend on Z. And, so maybe actually, yes. So the, let me just tell you, sorry, I forgot the, some of the, yeah. So why is this important? Oops. Okay, so what I want, I say there must be, these are the error correction conditions. What does it mean? Maybe I should go one slide. Okay, I say we can correct a set of errors if and only if. Now, what does it mean to correct a set of errors? I think I have to first specify that. And then you can understand what is necessary to be happening if I have to correct a set of errors. Now, what I want is the following. Now, I have to first erase this. This is going to go wrong. Okay. So what is correcting a set of errors? That there exists a reversal operator that maps rho back onto itself. So the idea is that I have a density matrix rho. Okay, so I have a density matrix rho, which has support only in this subspace that I've selected, in this code space. There's an encoded state. And now some super operator S happened, which is my noise. And now what I want is, or ask about whether there is another super operator, which is the reversal operator, which is a super operator. I think. So this reversal operator needs to be trace preserving. It's a real physical thing I have to be able to do. And this reversal operator should map this onto something that's proportional to rho. Why is that? This alpha is not necessarily the same as the one over there. That doesn't matter. It's just that because this is not trace preserving, I don't need this to be equal to rho. Yeah? So there's this constant. But I mean, in essence, if this is trace preserving, the super operator just needs to be moved back. This, of course, is a very special thing to happen, right? I have noise, I have a measurement happening, and I can undo it. Okay, this is what this is saying. Whatever the super operator, maybe the super operator came from some interaction with a bigger environment, and this environment had information, was collecting information of the system. Now I traced out over the environment. But it's a priori very unlikely that such a reversal operation exists, because we need to, typically, this type of dynamics is reversible. It's irreversible, yes? So we need to select our code space very precisely or very well in order for this operation to exist. So there must be dependence between the choice of the code words and the action of the errors. And that's what the quantum error correction conditions tell you. And intuitively, so this is why I was going to. So let's imagine the environment. This is just at the intuitive level, because we're going to try to show this in a moment. But let's look at this condition A. Let's imagine that the environment was measuring some observable B, by which the expectation value with respect to these code words was some constant that depends on which code word I had. Then I cannot, so the environment learned something about which code word I had, whether I had a 0 or a 1. Then I cannot reverse the error. Yeah? So, and this also corresponds to, connects to topology in some sense. Because in topological order and so on, you typically have a system where you say, well, I have a bunch of states. These are degenerate ground states of some Hamiltonian. And local observables are such that their expectation does not depend on what state I'm in. Yeah? It's independent, so this is not true. So it's some constant independent of Z. But you can actually rewrite the error correction condition in a slightly different way, in which you actually refer to indeed observables and their expectation values on the code words, and that they should be independent of Z. This is I think I referred to this in my review. This is something that comes out of a Gottesman paper. Okay, but in this form it doesn't quite look like an observable, this EK dagger EL, right? Because it's not necessarily Hermitian. Okay. Yes. So if alpha KL is a delta function, then you see that the error EL sends Z to some state, and the error EK sends Z to an orthogonal state, right? That's a delta function. So that's definitely a nice thing, because then I would be able to, tell these errors apart. But it's, your errors can actually have identical effect on a code word. The other way of looking at this condition is that, yes, so maybe let's see. Okay, I actually think I'm going to just prove this. I think that's more efficient than just talking about it. Okay, so let's do this now. Okay, is everybody still awake for a proof? Has anybody seen, nobody knows these quantum error correction conditions, right? Let alone the proof. So, okay, so we ask whether there exists a reversal operator. The reversal operator has to obey this condition. We have a P, which is the projector onto the code board, or sometimes PC for code. And, this is not a vector, sorry. Z bar. Does everybody know what I mean with this? This is important. If you're not getting this, this is the projector onto the code space, right? So you project onto the subspace And that projector can just be written as a sum of projectors on every, on a basis on this space. Yeah? So these are basis vectors. The reason that I'm mentioning this is because what I'm actually going to prove is this. There exists a reversal R for a set EI if and only if this holds something. P EI alpha ij, P alpha ij are Hermitian. This is alpha ij is a matrix, is a Hermitian matrix. Okay, so this is the form of the quantum error correction condition as you find it in Nielsen and Chuang. So I have a bunch of errors, EI, that come out of my super operator. And then I say I have EI dagger. So this is for all Lij. For EI dagger EJ, I put it in between the projector onto the code space. And this has to be equal to a complex value, which for alpha ij forms a Hermitian matrix times P. Yeah? And if you now start taking bras and cats with respect to these code words, you can see that this is equivalent to that. Okay, but I'm not going to show you that. So we say that, so this has to hold for all I and j in this set of errors. For I equal to j and I unequal to j. And it's also an if and only if, so it means that I have to prove two things. I have to say that if this is true, I'm going to give you what is the reversal, right? What operation reverses the error, undoes the error. And on the other hand, I have to show if I have a reversal, then we can derive this. Yeah. Okay. Now, I say that this is a Hermitian matrix, which means I can diagonalize it, right? So, so first I'm going to prove this. I'm going to prove from this to I'm going to construct my reversal operator. And I think this reversal operator gives you a very nice intuition about how we select this code space. Okay, so we have this is true for all I and j. And because this is a Hermitian matrix, I can diagonalize it. So there is a diagonal matrix D, which is U dagger alpha U. Right? And these alpha ij are just the entries in this matrix. Now, so I can multiply with U on these sides. And I sum over these i's and j's when I do this matrix multiplication. And I can absorb this in linear combinations of these e's. So let me just tell you, so I don't want to go through every step, but maybe you can verify this at home or just in the Nielsen and Chuang book. So Fm is a linear combinations of these Ej, but it's a linear combination such that these UJM forms a unitary matrix. And it's this unitary matrix. So if I can rewrite this condition as P F K dagger Fm P is equal to D Km P, where D is now the diagonal matrix. Okay, so maybe you want to spend some time verifying and do this for yourself, but maybe you're willing to believe that that's possible. So I just rewrote the error conditions in this different form such that if K is unequal to M, this is 0, right? Because this is a diagonal matrix. Yeah? Now, I want to make one more comment. So you said you know super operators. So if I have a superoperator with these operation elements or Krauss elements, I can also have a superoperator with these Krauss elements, right? And if you have worked with this, you know that these are the same superoperators. And you can relate these two. There is this freedom. Okay, so a superoperator has a freedom, which is a unitary freedom in this choice of these Krauss elements. Let's see. Maybe I want to say one more thing, is that what this also shows is that, okay, so I said, actually I haven't proved this yet, but I said this is the error correction conditions, right? Now, if this is the error correction conditions and these hold, then these also hold for this set F, right? Where F is this unitary mixture. Yeah, okay, actually, well, maybe I shouldn't say this is. I mean, actually, the error correction condition hold where I take F to be any linear combination of the EJ. Yeah? Why am I saying this? It's because if I can correct a bunch of Pauli errors, say I can correct any Pauli error on a single qubit out of n, I can correct any linear combination of these Pauli errors. Because of the error correction conditions. Because if I verify the error corrections for my Pauli errors, that's to say my Pauli errors, my EI dagger, EJ, are Pauli errors, and I know that this is true for all these EI, I, and J, then I take linear combinations of these, and I see it also true for linear combinations thereof. This is a specific linear combination that is it relates to this unitary, but you get a different matrix here for if you take other linear combinations. There's no constraint on this alpha ij other than it's Hermitian. Okay. Now, okay, so I'm here. So what do I want to do now? Okay, I'm going to use the polar decomposition of a matrix. What is the polar decomposition of a matrix? I have an arbitrary matrix. I can write it as a unitary matrix times a matrix J, which is defined as like this. There exists a unitary matrix, and then this object J that I can just calculate. And this J, because of the way I define it, it's clearly Hermitian and it is non-negative eigenvalue. So I can write J's. Okay, so I can do that. I can do that for this guy, FMP. Okay, so what is the polar decomposition? This is just an arbitrary matrix. This is my A. So there exists a unitary transformation. I give it a label M because it will definitely depend on this Fm, right? And then, okay, I have to take the dagger. So that's P dagger, Fm dagger, Fm P. Okay, P is a projector onto this code space. Its dagger is itself. So I just take out the, do some coloring here. So, okay. Okay, and look at this. P, Fm dagger, Fm P. I could use something over here, right? Because I have this. P, Fk dagger, Fm P, dkm. This holds for all km. And this is diagonal. So I can rewrite, I can plug this in. This is um on the square root of dmm p. So I have p squared, but the square root of a projector is a projector itself. Okay, so what does this mean? It means Fm on P is proportional to a unitary matrix on P. Yeah? So basically, you can write this as Fm on a code word. What does it do? It acts as some factor, some prefactor, times a unitary matrix. Okay, so the action of the error, right? Because Fm, well, it's a linear combination of the error, but it's you can, the super operator I was started with these operation elements, but they were equivalent to a super operator with these operation elements. And so these are equivalent set of errors. And the action of this error is just doing a particular unitary transformation. And I have not used everything, because this condition also said if k isn't equal to m, it's 0. Okay, what does that mean? So for k unequal to m, I have this thing, right? So what I can also rewrite, I can take Fm in the polar decomposition. I can do this for this guy too. It's just the dagger. So for k unequal to m, I have dmm dkk. I'm assuming this dmm is unequal to 0, of course, here. Otherwise, it's not relevant. Times p uk dagger ump is equal to 0. That's what this condition reads for k unequal to m. Okay? So the right-hand side is 0 for k unequal to m. On the left-hand side, I've used my polar decomposition, and I get it in this form. So what this says, you'd say, well, and I'm assuming these coefficients are non-zero, otherwise it's kind of trivial. But what this says in words that is that if I have my code space, so it's some subspace, there's some projector P, that for error k, this is mapped onto some other space by a unitary transformation. So this is like my F1 does this. My F2 maps it onto another subspace. And this condition says that these subspaces are orthogonal. And you can massage this a little bit by which you say this more clearly by taking bra and ket with respect to these projectors and so on. But what it says essentially is that each error maps you onto a different copy of this original space. And each of these subspaces are orthogonal. So all the vectors here, so I have my 0 and my 1 here, and any linear combination thereof. And see here I have my F1, 0, and my F1, 1. And here's my F2, 0, and my F2, 1, etc. And these are all orthogonal. And the same for my F3, etc. And then I think you can understand what is the reversal. So let's assume that these spaces, so this is the code space. And I can say, well, my operation F1 dagger maps it onto a space P1. So this is my space P1. This is my space P2. It's again a two-dimensional subspace. And so what I do, so in this, well, let's call this is the projector onto this space P1, which corresponds to F1 error have happened. So what I want to do is I first want to project onto one of these spaces, right? I'm going to do a measurement that says which of these errors have happened. And when I know that, I'm going to do reverse, because there's a unitary transformation that relates these. That's this unitary transformation here. Yeah, so now it may be, okay, so the reversal operation is now given by UK dagger PK sigma PK UK. And we assume, okay, so PK, so let's just write it down first. There's a lot on the board. Okay, so PK are the projectors onto the errored spaces, right? There's one error space for every error that I've had. And I'm assuming that the sum of these error spaces is the identity. It may be that, it doesn't matter, because it could also be, if it's not the identity, I'm starting with a two-dimensional subspace. There's a bunch of errors that happen. that map it onto other two-dimensional subspaces. Maybe the space is large enough that I don't fill it all up, and then I say, okay, I'm going to do a measurement to see whether I'm in that part of the space, which I'm not likely to get because there's no error connecting me to this, or I'm here. So I just do some measurement that determines which error space I'm in. Is this clear? Yeah, so if and then once I know that, I do a unitary transformation undoing the error. Now, you have probably heard from parity check measurements. So you could describe this as one big operation. With parity check measurements and stabilizer codes, this projection onto the error space is doing your parity check measurement. And saying, okay, let's say my error was actually a slight over rotation. And this is maybe not so clear in this. Okay, so I project onto certain error spaces if Pauli errors haven't happened. And then my unitary transformation, if a Pauli error has happened, is always a Pauli, right? Because if a Pauli error has happened, I can undo it by another Pauli. Okay, so maybe people are kind of... Any questions? I'm not done yet, but I'm barely scratched the surface of what I'm going to say. Anyhow, but is this, okay, so forget about the mathematical equation, it's late in the day, whatever. The thing I want to get across is that you set up your subspace such that the error operator maps you to other orthogonal subspaces that are related, by unitary, and you have to just know which error space you're in. Yes. What do I want to say about? One can also, maybe I want to make one comment about this also, that often, this is a code space. But if this error happened, this is also a two-dimensional code space. Yeah? And this is typically also a good code space. As long as I know where I am, I actually don't have to reverse the error. And this is very much true if you look at stabilizer codes, which we'll do in the next lecture. You actually don't need to correct your error. As long as you know what happened, you remove the entropy, right? We're no longer ignorant about what happened. That's all we need to do. And as long as our qubits are still protected, that's to say if more errors happen, they have this code space that we're working with now has the same properties in the sense that new errors will map it onto orthogonal spaces. Right? Okay, so let me finish the other part. Okay, so what I've shown now is that if this is obeyed, there is a reversal operator. And now, of course, I need to do the opposite. If there is a reversal operator, some kind of trace preserving superoperator, I need to show that this condition needs to hold. Okay. Okay, I'm going to do that here, and that is would be the end of today. Okay, we hope we can do that in this amount of space. So imagine there is a reversal. And this reversal is given by, again, some superoperator with these operation elements. And what is the property, what does it mean that there's a reversal? Okay, so I have a density matrix rho. Now, if it's an arbitrary state, I don't know, it's not necessarily in the code space, right? So I'm putting a projector here such that this object, it may not have trace 1, but it will be something in the code space. It only has support in this two-dimensional, say, subspace. And now I have errors happening. This is my error map, right? And now I apply my reversal operation. And now that reversal should map this input back to itself. So this could be some constant P rho P. Yes? And it's a constant because E didn't need to be trace preserving. So it doesn't need to be quite identical to P rho P. And this has to be true for all rho, because I can do this for all rho because I project afterwards in the code space. So. Okay, so what do we have here is we have this thing. I could call this a super operator with elements aij. I'm including the P. So I could write this as a sum over ij, aij rho, aij dagger. And the aij are rj ei p. And this says that this has to be C P rho P. And so I have some super operator with these Krauss operators or operation elements. It has to be actually all of these have to act like P. Right? Because the whole thing, and this is again something that you can, more rigorously prove. If you have two super operators and this has to be true for all rho, then these aij have to be proportional to P. Maybe with a coefficient that depends on ij. Because the overall action is that of doing the projection onto P. Okay, so we just take that to be, we're not going to go into why that's, if you work with, I'm not going to prove that this is absolutely needed, because then I would have to go into more super operator stuff, but I think maybe intuitively you understand this, that every one of those guys has to act proportional to P, and there is a freedom of a constant Cij. Okay, I got that. Now I take the dagger, so that's P, Ei, J dagger, Rj dagger. This is P. This is a complex conjugate. Why am I doing this? Because I want to rewrite these conditions. Now I'm going to take this guy and put it in front of this guy, and then sum over j. So I'm going to do this. Ej, we're almost done. P that's just, this and that. So I can use these inequalities to say that this is sum over j, ckj star, cijp. And I can use sum over j, rj dagger, rj is the identity. Agree? Because that was a super operator which obeys this condition. So this is P, ek dagger, ei, p. And this I can rewrite. This object is just some alpha ki p, where alpha is Hermitian. Which can be verified because it comes out of this thing. Okay, so that's what I wanted to do. There is a reversal operator. Because it's a reversal, it has to obey this property for all rho. That implies something about how this joint super operator of the projection and then the noise and the reversal acts. It acts very simply. It acts proportional to P. I got that. I manipulate a bit, use the fact that it's trace preserving, and I get the error correction condition, as we stated. Okay, so that's, I think, yes. That takes a long time, these kind of things. I hope that was of some use, because I think there are cases in which the noise model that you have is, if you want to analyze the effect of error correction, you should use the error correction conditions, perhaps. And you should also think about approximate error correction. But we'll go to that in the next lecture. So in the next lecture, I want to discuss some simple codes. So I want to discuss the 3-bit repetition codes. And connected maybe to the recent experiments that some of you may know more about than me, perhaps because if you've worked on these experiments. I also want to talk about the amplitude damping noise, which is described by a map. You know, amplitude damping is basically T1 noise at a very low temperature. So amplitude damping noise is a, does that ring a bell if I say amplitude damping? No. Okay, so amplitude damping is a noise process. I have a qubit, and the noise is such that 1 decays to 0, but you know, 0 is never going to go back to 1 because I'm at fairly low temperature. So I can give you a simple super operator that does that, yeah? And there's a certain rate at which this 1 goes to 0. Now, that is not a poly channel. This is not a mixture, or that super operator is not a mixture of polys. And there is a special 4-qubit code that can correct a single amplitude damping error, whereas no 4-qubit code can correct for single qubit poly errors. Yeah, so I want to discuss that. Okay, are there questions right now? So if you want to know about this error correction condition, you just look at Nilsson and Chuang, and you can, you know, so verify the proof and so on. Yes. Okay, that's it. Turn off the thing.